expensive in terms of computation resource consumption. So how can we actually enable AI inference and AI power in blockchain directly? That's the question, right? So now, oh, do I have a clicker?
Why they bring down?
So, but that is a fundamental challenge because blockchains are not really set up and built for this type of a heavy and data-driven computation, because fundamentally blockchains are replicated computing and replicated storage. Even if you have layer 2 scaling and layer 2 scalability, it is still rooted in the layer 1, which is run by consensus and extremely expensive. So what we need to do here is to actually change how we build applications and how we build decentralized applications as overall. And fortunately, we have some previous experience from the Web 2 that we can borrow. So in Web 2, before 2000, the entire Web 2 and internet is built based on this very synchronous architecture, where you have a web server that does really everything, from request handling, access control, computation, data access. Everything's done by this one single web server. It was very clear back then this type of architecture will not be able to scale to the level of user growth that we've seen in internet growth. So what happened? What happened is that my clicker doesn't. Oh yeah. All right. Okay. So what happened is that over the last 20 years, we actually moved into this modern web architecture, where the web server itself is just acting as a coordinator, where it receives requests from users with high concurrency and high scalability, and send all of those requests to specialized backend services such as AI, big data service, data base, and authentication. And all these specialized backend services will do the processing and send back callbacks so that the web server itself can coordinate and assemble a request back to the user to build a coherent Web 2 experience. So, if we look at Web 3 today, the problem is the same. The architecture problem is the same, where we have smart contract platforms in blockchain that are just monolithic Web 3 servers. It can only do very simple computation. And if you look at all these smart contracts today, they have very, very limited data access capability. There's no way they can, for example, in smart contract, access a user's historical behavior, such as if the user traded in Uniswap before, in the past, you cannot actually get that data from smart contract in blockchain directly. So, we have a problem. Well, to illustrate with this with a very, very simple example, if you want to build a trader loyalty program today on chain in smart contract directly, say you want to say, okay, this user traded more than $30 million volume in the last 30 days. In the next 30 days, I will give you him like 50% trading fee discount. If you want to build this type of feature directly in smart contract today, it will cost you 8 hours of block time and 40K in transaction fee to just get the computation done for a single user about this kind of a single user trading volume on chain directly. Because there is no trust-free access and computation on historical data on chain data today. So what Brevis is trying to do is to introduce this modern asynchronous architecture to blockchain applications as well, where the blockchain itself will be treated as a simple and very lightweight web server that handles all the asset-related computing, and it will be the coordination point of all the computation, off-chain computation resources, such as ZK Data Coprocessor, ZK ML, and ZK VM. So how does this work? We'll just give you a very, very concrete example using our ZK Data Coprocessor. So what is a ZK Data Coprocessor? It is a piece of software that can generate ZK proof for any arbitrary computation on any kind of historical on-chain data, and send that data back to the blockchain smart contract so that blockchain smart contract can verify that easily and with low cost to directly use that computation result in the smart contract directly. So building with Brevis is actually very simple. Now, instead of writing very complicated, very high-cost code in the smart contract to access the historical data, you can just write some off-chain code to say, these data are the data that I want to read, and this is the logic that I want to do the computation for, and finally, the entire Brevis software stack will generate the ZK proof for you, so that you can send it back to the blockchain, so the blockchain smart contract can directly process and do the business logic you want. So what kind of data that we support today is that we support storage state, block information, transaction receipts, which are essentially events, and user behavior, and also beacon chain state, transaction account, and all of these information. And you might ask, okay, so what is different between this versus using a data indexing solution? If you can use a graph, you can use geoanalysis to get the same data, but what's the difference? Well, the difference here is the ZK attestation. So using Brevis, you can have an end-to-end encapsulated ZK proof showing that the data you gathered in the first place and also the computation you run on these blockchain historical data are all correct. And therefore, for the entire cycle of your application, you're not introducing any other additional trust other than the blockchain itself. So that's the power of ZK Coprocessor. Now, after you get the data with very, very simple API, we present with you a very easy to use data stream like API, where you don't actually need to learn anything about ZK circuit building. So you're just dealing with this data using map, reduce, group by, filter, zip, all these very, very nice kind of primitives to compute whatever the data logic you want, such as trading volume and everything. And then finally submitted the result back as a callback function to the blockchain smart contract, where you can do the business logic in the smart contract directly. So to build the same thing with Brevis, now using for the kind of trading volume discount feature, instead of doing everything on chain, now Uniswap contract or any DEX contract can send a get trading volume request to the off-chain world, where the off-chain computation can happen, end-to-end encapsulated with ZK proof and send back the result to the blockchain, showing that what is each and every user's trading volume for the last 30 days. And after that, you can build kind of a trading fee discount feature with things like hooks, with things like plot links. To do that with like millions of to do that for a single user across millions of transactions on Uniswap, it only costs you about 20 cents and 24 seconds latency. So Brevis SDK is publicly available and ready to use. In fact, we already have a lot of different partners that are building similar features to this type of data-driven DeFi features. For example, we recently launched on mainnet with one of our partners, Quanta Network, which is one of the biggest perpetual swap aggregators on Arbitrum. And they can actually process a large amount of data and generate proof for VIP status and get fee rebate for market makers. So as I mentioned, one of the biggest use cases for Brevis is data-driven DeFi, where you can do a lot of data-powered and data intelligence, even AI-related things to power your DeFi application and customize user experiences based on their historical behavior. This is extremely powerful because this is something that has been missing in Web3 forever. But if you look at every Web2 applications, you have this kind of features available. So, and we're also working with a bunch of consumer-facing applications such as gaming, which is also a very big category where you want to customize user behavior based on user experience, based on their user behavior and user profiling. And finally, there are a large class of data and computation-powered infrastructure where this infrastructure requires trust-free access to the historical blockchain data, such as like in the MEV space, we work with a bunch of partners in the MEV space to empower them to build more efficient block data marketplace. So just one final point to touch on. So we started with a pure ZK model, but we also add an optimistic co-processing model with ZK fraud proof. So instead of relying everything on ZK, you can choose to use an optimistic co-processing model where there is going to be an eigenlayer ABS that generates all the co-processing results first as a proposal to post it on the blockchain. And if the result is wrong, during a challenge delay, you can actually submit a ZK fraud proof to challenge that particular result. So that way, we offer a very comprehensive trade-off space for developers to choose with an option to have lower cost than using pure ZK, and very importantly, also enable more features such as proof of completeness and proof of non-existence. And generally, it's much more secure than simple proof of stake because you don't actually reduce the security assumption as there is the final defense line of ZK proof as a fraud-proof mechanism. So yeah, with that, I conclude my presentation, and thank you all. Feel free to ask any questions offline.